Okay, kids, we're back and we're into chapter 10.1 section there, and we're moving forward from our discussion about light being an electromagnetic wave, where there is an oscillation of an electric field, which leads to an oscillation of a magnetic field, which leads to an oscillation of an electric field, and that's what light is. Now, the field that's easiest to see how it interacts with us and with the matter is the electric field. So here's what I've drawn a picture here, and you've hopefully have watched the videos, okay? Uh, most naturally produced light has an electric field that is in a random arrangement. So if you have a light bulb producing light, depending on which part of the light bulb's light producing mechanism, which atom is producing light, it's quite random. And I've drawn that here, red electric field, with light in a variety of different electric field orientations. That's what this um, cluster, if you will, of red arrows represent. Unpolarized light, light with random electric field orientation. Well, then it can go through a material called a polarizer. I hope you saw that in the videos. And polarizers have something called a polarizer axis. And only light with with electric field that is aligned with this axis will get through here. And that's what I've drawn here. Only light with electric fields with this orientation got through. Now, these polarizers are materials, they're devices that polarize light, only allowing light with a certain electric field orientation to get through. Why does this happen? Well, let's find out. So let's say we have a slab of a material, maybe a piece of plastic that's a polarizer. And if you were to take a look at the polarizer, it's made of very long molecules like this. So if you've got a light with an electric field of this orientation coming in, it will hit one of these long molecules, this electric field, and it will cause electrons to move up and down the molecule because there's freedom to do that. So the electron does work on the electric field does work on an electron along the molecule. So we can say that since that electric field did work on an electron by moving it up and down one of these molecules, that it has been absorbed. Now, if you have light that's perpendicular to the molecule in terms of its electric field orientation, so here the electric field is this way, it can't push an electron up or down. So the electric field of that light is not absorbed. So that electric field and that light gets through. And that's what I've drawn here. Look, electric field with this light doesn't exist on the other side of the polarizer. Light with this electric field does get through. Light with that electric field does not get through. So what do we establish here? We establish this direction right here, which is the molecular axis. This polarizer material is made of molecules that are aligned up and down. And I have this stuff in the class, and we would have done some experiments with it, but here we are instead. Another way of describing this polarizer molecule is by its polarizer axis. It lets light that is aligned with an electric field in this direction here to get through. So the polarizer axis is actually perpendicular to the molecular axis. This is what is its structure. This here, the polarizer axis, is what type of electric field light gets through. Now, I hope you watched the video because you saw this in the video. Here's light with electric field in any direction. Just this unpolarized light right here. It hits some calcite, and boom, all of a sudden, and we learned about refraction in grade 10, the light bends as it hits the light, this mineral, and it's actually split into two because the electric field here is in this direction, so light with this electric field bends at this particular angle, And here we have electric field like this, so light with this electric field bends at that particular angle. So I've kind of redrawn it for you. If you've got unpolarized light, so light with electric field up and down and light with electric field left and right, it comes in, but it splits. Light with up-down electric field only bends with this angle. Light with left-right electric field bends with that angle. So you actually see two images. And I hope you saw that in the video that the professor, I think he was a geology professor, showed. If you put, and I would have done this in class, we would have walked around to different stations to get this done, but here we are. We're watching it on YouTube. And you put a piece of crystal over your textbook and look at the writing, and you would see two images, right? The unpolarized light would be split into two kinds of polarized light. Unpolarized light split into two kinds of unpolarized light, each with perpendicular electric field orientation. You can also get polarization by reflection. By reflection, this is something you would experience as glare off of a tabletop, off of plastic, off of water, off of snow, off of clouds. And we would have walked around at different stations and noticed that reflection is definitely polarized light. You'd get unpolarized light from a source. It hits a surface and is reflected, but the reflected light is polarized, meaning only light of a certain electric field orientation is reflected. The other light with the other electric field orientation is absorbed. It works, for example, with air and water. All right. So the amount of polarization depends on the material. Is it air to water, air to snow, air to plastic? What is it? And the incident angle. The amount of polarization you get depends on the incident angle. And I hope you saw that video. Now, the angle of incidence which produces maximum polarization is known as the Brewster's angle. That's the person that did the investigation here. So there is an angle where you will get maximum uh, polarization. Okay, kids, so a lot of videos to watch today, but it's very much an experimental thing I'm trying to demonstrate to you. All right, we're going to keep on working, kids. Okay? We need order, regiment, and discipline. Okay? You guys are going to university next year. We just got to keep on going. You might not like me now because I keep pushing, keep pushing, keep pushing. But, when you're sitting in your first year university course, it's, yeah, Brewster's angle. I saw that before. At least you can say you saw it before. At least you can say you've gone through some of this before. So everything you experience will not be brand spanking new. Okay, so I'm really trying to get you to see as much of this as we can as we move through the month of June. Plus, there's no exams, so let's just keep learning. Don't get lazy. Okay, you get lazy, it leads to failure.